Hi all. Okay, so in previous class we were studying about properties of relational decomposition. So in that, total five properties are there. So already we have seen three. So that is attribute preservation, dependency preservation, then non-additive joint property of a decomposition. These three things we studied. So here in third one we have one algorithm also. So to check is it a lossy or lossless joint. Okay, so that is the non-additive joint property it's holding on. Okay, so that algorithm also we have studied. So now we'll go ahead with fourth one, that is testing binary decomposition, and fifth one successive non-additive joint decomposition. These all things already we have studied. Two examples we have taken for the third property. Okay, so for property that is testing binary decomposition for lossless joint property. Okay, so here it's nothing but whatever relation is there, that relation we want to decompose into two tables. Okay, there is nothing but binary decomposition we want to do. Suppose if I have as R, okay, so I want to decompose this one into R1 and R2. Okay, R1 and R2 I want to decompose. So this R1 and R2 after decomposing it's a D. Okay, so both together we are saying that it's a D. So now this one we want to test it, that is a testing a binary decomposition for lossless joint property. So is it a lossless or lossy? We have to check it. So instead of running that whatever previous one algorithm was there, the entire part, so there is a one more alternate method, easiest one. So there we can see is it a lossy or lossless. Okay. So here this is nothing but whatever functional dependencies you have. Okay, so here functional dependency F, okay, on R. Okay, so the this should have some property. Okay, so depending on this one we will be having some property that will check it. Okay, so what is that is, suppose a decomposition D, okay, R1 R2 of R has a lossless joint property. Okay, so with respect to a set of functional dependency F on R. Okay, so if and only if either, okay, so if it's in whatever decomposition we do it, that is we'll say as a, it's a lossless. Okay, so either of these two things are holds. Okay, so what is that is R1 intersection with R2. So whatever will get the here attributes, that attributes if it is derives R1 minus R2 attributes. Okay, and this whatever functional dependency will come, okay, it's R1 minus R2 to sorry, R1 intersection R2 to R1 minus R2, whatever functional dependencies will come. So these functional dependencies are there in F plus. Okay. So, or same thing here, intersection again, that is R1 intersection with R2 derives R2 minus R1 is in F plus. Okay, so what is this logic is, suppose if I have as a two things, that is decomposed into R1 and R2. Okay, so if I did intersection of this one, okay, so I'm doing the intersection of this one, so there should be some attribute common in between, and from that I can derive some other attributes. Okay, so what all those attributes is nothing but here what will come in R1 and R2. So whenever we will do decomposition properly, that time always for the joining purpose of these two relation R1 and R2, common attributes will be there. That common attributes is nothing but primary key, foreign key. Okay, so one side it may be a primary key, one side it may be a foreign key. Okay, so two tables they are connected with each other by using primary key and foreign key, so that whatever attributes same are there, in one side it is a primary key, one side it is a foreign key. Okay, so only that attribute will come here. Okay, so only that attribute after intersection it will come with. So from this attribute, okay, so there is nothing but it's, I can say as a, it's a primary key only it will be there, or in general if you are saying is it will be a candidate key. Worst case it will be a candidate key. So from this candidate key, so can I derive, okay, so from this candidate key can I derive R1 minus R2. Okay, so R1 minus R2 means in R1 whatever attributes are there, those who will keep it, minus which are not there in whichever are there in R2, that will remove it. Okay, so whatever is there, this is nothing but all the attributes you can derive, because after intersection whatever here this side R1 minus R2 will get it. So here list of attributes are there in only R1 will get it. So if it is able to derive it after intersection, it means so all the attributes were covering of R. Okay, indirectly we are covering of R. So or it will be there as a R2 minus R1. Okay, if it is a primary key of R1 or R2, depending on that we have these two things. So depending on that you will get the decomposition properly. If it is decomposition is properly happened for a binary decomposition and it don't have the lossless property, okay, it always it will come as here whatever attributes are there in only R1 or only in R2, it will match it. That interaction will automatically it will match it. So this is the fourth property. Okay, so fifth one study, that is successive lossless joint decomposition. Okay, so here what we are doing is, so already you have joint property. Okay, so whenever you will what this will claim is preserve the non-additive in successive decomposition. So once already you have decomposed, okay, that is maybe R you decompose into R1, R2, R3, R4 like that. Okay, so that is R1 to Rm we written. So in this again maybe one table again we want to decompose. Okay, one or more than one table. Okay, so that is nothing but here suppose I want to decompose again R2. So this R2 again I am decomposing into Q1, Q2, Q3, Q4 like that. Okay, so after that whatever nth number of iterations we will do it, so that successively whatever we are decomposing it, those all tables should have lossless decomposition property. Okay, so for example if you remember whatever examples we studied in 3NF. Okay, so normally R was there, so we used to decompose into suppose T1, T2, T3. Okay, so maybe that time T1 and T2 will be there in third normal form. Okay, but T3 will not be there in third normal form, it will be there in 2NF. Okay, so what we'll do is T3 will decompose into T3A, T3P like that. It will decompose. So that is a successive decomposition. We are doing it for the T3 table. Okay, so that whatever decomposition we are doing it. So finally, all the tables, whatever we get it in the end, after n number of iterations like that, we can decompose. So finally, whatever we will get that all the tables that should have lossless joint decomposition. Okay, so lossless property it should be supported. So this is successive lossless we are saying. Successive lossless in the sense whenever we are doing n number of iterations, that time also lossless joint property should be there. Okay, so this is the same as that of whatever we studied previously, but this is a number of iterations are more here. That's it. Okay, so these are the five properties of our relational decomposition. Okay, so now we'll go ahead with some algorithms. Okay, so here for them before going for exact algorithms, some definitions will study. Okay, so that is equivalence of set of functional dependencies. Okay, two functional dependencies. Okay, set that is E and EF suppose we have. So when we'll say both are equivalent or not, we'll check it. Okay, so for this equivalence set we require one more thing, definition is a cover. Okay, so before studying this equivalence we require as a one more thing as a cover. Okay, so what is cover is nothing but here a set of functional dependency. Okay, F is said to cover another set of functional dependencies E. Okay, so F covers E, we are saying it. Okay, so F it covers E if every FD, okay, if all the FDs, okay, so each and every FD whatever belongs to in E is also in F plus. Okay, so whatever E has, so those all functional dependencies are there in F plus, means I can say as a E covers sorry F covers E. Okay, so here we written definition for F covers E. Okay, so alternately we can say as a this is a E is covered by F. Okay, so reverse way we are saying is a E is covered by F or F covers E. Okay, so whichever you want to call it. Okay, so here what we are doing is some functional dependencies will be there. So for a E, okay, and F also. So now we are identifying the for F plus we are identifying, we are writing the all the things. F flow plus is nothing but F closure. Okay, so this is all closure property we studied. So here F closure will identify. So F closure how will identify is nothing but after using the inference rules. So whatever inference rules we have, so whatever FDs we have, so on top of that we'll apply all the inference rules, then we'll get the F plus. So all F plus we'll be having. So then E we have whatever we, so E whatever set is there, that set FDs are there in F plus or not, we'll check it. If it is there means we can say as a F is covers E, otherwise we can say as a F is not covering E. Okay, that's the definition. then we'll say as a what is equivalence. Okay, so here what we are saying is a two set of functional dependencies E and F both are equivalent if and only if that is E plus is equal to F plus. That is nothing but two sets we have E and F. Okay, so both are the functional dependencies. Now we are identifying the closure of E and closure of F. So both are equivalent means we are saying as a both are equal. Sorry, if, closure of E and closure of F both are equal means we are saying as a both are equivalent. Okay, so indirectly we can say as a F covers E and E covers F. Both are equivalent means we can say as a the both the FDs, okay, that is FD sets E and F are equivalent to each other. Okay, so just we'll take one example. Okay, so for example, okay, so here to take the example. Okay, so we should have so normally we should have E set, F set. Okay, so in both the sets some functional dependencies will be there. So what we can do is we can identify the closure of both the sets. Okay, E closure, F closure, both we can identify. Then one by one we can check it. It's there in both should have same FDs or not. Okay, so otherwise from one by one we can check it and we can say it covers that under set or not. Okay, so like that we can check it. So just to take one example. So here, okay, so in this one, what we have is functional dependencies, two functional dependencies we have. Okay, so F is F and G, two functional dependencies we have. So F contains A to C, AC to D, E to AD, E to H. Okay, and one more we have is A to CD, E to AH. Okay, so what we can do is so one set of functional dependencies we can take it. Okay, so that is maybe we'll consider as a G now. Okay, so from G, so whatever here functional dependencies are there, from this we'll see can I cover all these functional dependencies or not. Okay, whatever F contains, can I cover all the functional dependencies or not, we'll check it. Okay, so here in G what is given is A to C D is given. Okay, so that is it means A to C I can achieve it. Okay, so this side we have to just see the inference rules and we can achieve it. Okay, so just we can see as a so A to C I can achieve it. Okay, because two set of attributes are there here, two attributes are there, so only one I can achieve it, that is A to C I can derive it. So that is this functional dependency I can achieve it. Okay, so now here if you saw have then E to A and E to H also is there. Okay, so here E to A is there, E to H is there. Okay, so these things also I can achieve it. So just we have to see E to D I can achieve or not. Okay, then AC to D I can achieve or not. So these two things I have to see it. That is E to D. Okay, because E to A we have seen. So E to A here also there, so I can achieve it. So it means here also E to A I can achieve it. So that part is over. So E to H, so E to H I can achieve it. That part also over. So here EC to D I can achieve or not, that I have to see. Then E to A I can achieve, sorry, E to D I can achieve or not, that we have to see it. Okay, so what we can do is here we have here AC. Okay, so that is if you saw here A to C is there, so here if I replace C instead of A, so it's same thing only. Okay, in this set I have A to C. Okay, so that is nothing but what we are saying is A can derive C. So here this C I can replace by A only. So A it's nothing but twice giving the same value of A, and I can achieve the D, or only if I given A also I can achieve the D. So it means here I can get the FD. Okay, that is nothing but A to D. Okay, so if I apply to the inference rules, so instead of this FD I can get as A to D. Okay, so in F I can get that is A to D. So here if you saw A to D I can achieve it. So this is nothing but G is covering the F here. Okay, so only it's left with E to D part now. Okay, so here if you saw A to D is there. Okay, so here E to D here we have. So here we can see we have E to E to D or not. Okay, so here we have E to D. Okay, so from this we have to see E to D we can achieve or not. Okay, so here what we have E to A we have. Okay, and here A to D also we have. Okay, so if I apply the transitive rule, okay, that is E to E to A to D, so it means E to D I can get it. Okay, so just I will revise once again. So I have to achieve E to D. Okay, so in this only left out FD is E to D. Okay, so now I have to check it here. E to D I can achieve it by G or not. Okay, so that is E to A I have. Okay, then A to D I have. Both are there. So if I apply transitive rule, that is E to A is there, A to D is there, means E to D I can get it. So that was only was pending here. So I can achieve this one. So I can say as if F is covered by G. So same way we can see for F to G also. So is it G is covered by F or not? So like that, if you got the functional dependencies, then we can say as a both, that is F and G both are equal. Or you have to do as a F plus and G plus, you have to apply all the inference rules. So whatever set of FDs will come, so those all things you have to list it, then you have to check it. Okay, so if you saw here, one more thing is, so n number of functional dependencies we can write it. So okay, so here n number of functional dependencies we can write it, but all those things are required in my database or not. Okay, so normally if you saw here A to C we have, okay, then AC to D also we written. Okay, so just now we proved as a this is a overhead, that is directly I can write as A to D also, because here C you can replace it. Okay, then A to D also I can write it. So instead of these things continuously, so n number of like this functional dependencies will come. So instead of using these things, what we can do is whichever minimal FDs are required, that FDs if are written in my F, so that will be enough for my database. Okay, so from that, whatever I required functional dependencies I can derive it. Okay, so whichever minimum is there, that if I return, okay, so that FDs if I return, that we can say as a minimal set of functional dependencies. Okay, so in my database while designing, if I return whichever functional dependencies are there, so maybe n number of things are there, in that whichever minimum are there, that if I saw it and if I return that one, so that will say as a minimal set of functional dependencies. Okay, so how to achieve that one? Okay, so it's nothing but you may have n number of things. Okay, so in that maybe some redundant are there. Okay, so unwanted FDs also there. Okay, so those things I have to remove it. So waste of keeping those things FDs. Okay, so what we have to do is always we have to find the minimal set of functional dependencies. Okay, so how we can achieve it? For that we have one algorithm also. Okay, so here just we'll study. Okay, so here, so this is a definition of minimal set. Okay, a minimal cover of a set of functional dependencies. Okay, this is a cover we are saying it. Okay, so whatever cover we studied here, this is the cover. Okay, so cover is nothing but one cover for the another set. Okay, so one set covers so one more set. So same thing we are saying it here. So so a minimal cover of a set of functional dependencies E. Okay, so this is a minimal cover is a minimal set, and this is only a minimal set of functional dependencies. Okay, that is equivalent to E. Okay, so what is minimal cover is nothing but here in this this is there in standard form, that is canonical form. Okay, what is canonical form, we studied. Okay, and without redundancy, that is means, so if I removed any functional dependency from this set, means our overall functional dependency rule, whatever we given, it will not stand as it is. Okay, so there will be always a shortage or there will be a problem. So this whatever set we have, so from that set I can't remove anything extra. Okay, so that is a minimal thing we should have there. So how to achieve from the given functional dependencies? Okay, so for that we have the one algorithm. So that is nothing but we'll say as a finding the minimal cover f for a set of functional dependencies e. So already e is given, from that we are going to identify, that is some set of minimal cover. Okay, f we are going to identify it. Okay, so what we will do is, here this is the input. So is nothing but one database, you will write the just some fds. Okay, so normally fds whatever you will see in your database, so all things you will write it. Okay, so for that database now we will identify the minimal cover. So whatever you will write, all the fds that will be there in e. Okay, so now we have to identify, there is one set, that is minimal cover, that is ef. So what it will do is, so initially it will take all the things. So whatever we written in e, so all the things will be taken in f. Okay, so now we'll see, is it there in standard form or not. So all the in f, whatever functional dependencies are there, so all are there in standard form or not, we'll check it. So what is standard form is, I think we'll say as a canonical form. So suppose one fd, that is x2, a1, a2, a3, like this, you have n number of attributes in the right hand side. So whenever you will write the functional dependencies, if you have right hand side n number of functional dependencies, those all you have to remove it and you have to keep it separately, different fds. Okay, so for example, if I have say x to a b c, so then we have to write it as a x to a, x to b, x to c. Three fds we have to make it instead of one. Okay, so that is, we will write it here. Okay, this is a common general definition we written, x to a1, x to a2, x to an, like that we have to write it. So this is a one step. What we'll do is, we'll perform the this is the thing. Listen, in f we'll modify, if any functional dependency has right hand side more than one attribute, those all will replace by 111. Okay, so always you should have right hand side only one attribute. Okay, so these are the one attribute we have to have it. Okay, then what we'll do is, for each functional dependency a to a, sorry, x to a, okay, in f, so whatever functional dependencies will be there in now f, so in that one by one we'll check it. Okay, so again in that one by one, whenever we are taking it, so we'll check each attribute b, that is an element of x. Okay, so now we are saying as a, in that one element b, called as a b, so it is a part of x. Okay, because we are saying as a, there is an element of x. Okay, so here if it is a part of x, suppose here x itself is a one attribute, so no need to perform this task. Okay, here if this x is contains only one attribute, no need to perform any task. Suppose if it is not a one attribute, so more than one attributes are there here, so then in that I will choose one, that is we'll call it as a b. Okay, then we'll see this condition, is it true or not. Okay, if it is true, we'll perform some action. Okay, so what is this condition is, so here whatever functional dependency we are taken it, from that what we are doing is, so if we are checking here, okay, so what we are checking is f minus this functional dependency. F minus means we will remove that functional dependency from f. Okay, and we'll perform the union with, that is nothing but we'll add one more functional dependency. So whatever functional dependency here is there, that will remove it. Okay, given functional dependency we'll remove it and we'll add one new functional dependency. What is that is, so in x whatever b we identified, that will remove it. Then x contains more than one attributes, so in that one attribute I'm removing here now. Then this can derive a or not, we are checking it. Okay, so if it is deriving, that is nothing but we are adding that one, so entire f whatever we get it, is it equivalent to f or not. So after removing this one attribute from x, okay, so and adding that new functional dependency, whatever we get it here, we'll add it to the f, then is it equivalent to f or not, we are checking it. If it is equivalent means, what we'll do is, then we'll replace x by a, x derives a, that will replace it by, that is x minus b. So whatever we remove this attribute from x, and we'll keep this entire functional dependency in f. So So this will continue for all the functional dependencies. So one by one we'll check it. So whenever we have left hand side more than one attribute, for those all things we'll do it. Okay, so after this we'll be getting the sum set again. Okay, so some set of f will get it. Okay, so in this thing, so one by one functional dependencies we'll remove it. This is the next step, fourth step. Okay, so for each remaining functional dependencies x to a in f, so what we will do is, if I remove this functional dependency, then still this is it equivalent to f or not, we'll check it. If it is equivalent, then I will remove that one, otherwise I will not remove it. Okay, so indirectly what we are doing in this algorithm is nothing but one by one elements of x here, that is if the functional dependency has more than one attribute in left hand side, one by one we are trying to remove it and we want to check it. Okay, so after that what we are doing is, so here next step, one by one functional dependency only we are removing it and we are checking it, is it equivalent to first normal form, sorry, is it equivalent to functional dependency as it is or not. Okay, if it is equal we'll leave it, otherwise okay, we'll keep on checking it and we will keep on removing it. Okay, so that thing will do it. So just we'll see one example. Okay, so here given thing is B to A. Okay, so D to A is there, B to A, D to A, then AB to D is there. Okay, so three functional dependencies is given. So this is E is given. So now we have to identify minimal cover for this E. Okay, so starting what will be there, my F will contain all these things. Okay, so F or some textbooks will say as a, instead of F they will say as a E dash. Okay, so that is a minimal core whatever you are identifying. Okay, so here it may be F or E dash, you can consider it. Okay, so here, so my new F is nothing but that is this entire thing. So in this I have tried to identify minimal cover. So now we have to, what we have to do is we have to apply for, this is the first step. Okay, so I took it as all entire F only. Okay, so second step, is it there in canonical form or not, we have to check it. If it is not there, then what we have to do is just we have to perform the operation, that is nothing but we have to form this one into canonical form. Okay, so here canonical form, so right hand side only one attribute should be there. If we saw this first one, right hand side only one attribute is there, this is fine, no problem. Second one, right hand side only one attribute is there, no problem, fine. Third one, right hand side only one attribute is there, no problem. So all these three FDs follows the second step. Okay, so we don't have any problem in second step. Okay, so this will remain as it is. Okay, so no changes in second step. Okay, now we'll go for third step. In third step what we are doing is we are taking one by one functional dependencies and we are checking any B attribute is there in left hand side or not. Okay, so that means more than one attribute should be there in left hand side. So if you saw functional dependency, only one attribute is there, so no need to take this one. So here if you saw second one, here also only one attribute is there, so no need to take this one. If you saw third one, we have two attributes. Okay, so we have to modify this one, or we have to check, can I remove this one and can I get the something extra. Okay, so in these A, B, so in this can I remove any attribute and can I get the something extra. Okay, so that we have to check. That is, instead of this one AB to D, can I get A to D or can I get B to D. Okay, so this is what we can get it, A to D or B to D, who will get it or not, that will check it. Okay, so what will do is first operation will try to identify, can I get remove the A or B, anything one of that we have to remove it. Okay, so here if you saw it, so I have already, that is B to A already given is there, B to A already given is there. Okay, so now both sides here I will add B. Okay, so in this functional dependency both side I will add the B, so that is I will get the BB to AB. Okay, so this is equivalent to twice giving the B and identifying AB. So it's nothing but only once if I given B, so I can identify AB. Okay, so it is equivalent to B can derive AB. Okay, so if you saw B to AB is there, now we got as a from this functional dependency what we got is B to AB, and here AB to D is there. So what it means is, so B to D I can get it. It's a transitive dependency. Okay, so B to D I can get it. B to D I can get it. It means I can remove the A. Okay, so this A I can remove it, then B to D I can get it. So now my new F will be, so that is B to A, D to A, then B to D. Okay, that is B to A, D to A, B to D. These things I will get it. Okay, this is the third step I have applied. Third step, then I got that one. Okay, now fourth step, what else there is? So any of the one functional dependency, we'll try to remove it, one or more than one. Still, is it equivalent to F or not? We'll check it. So here, whatever FDs we have, so one by one, can I remove this one? Can I remove this one? Can I remove this one? Like that, we have to check it. So for all the FDs, then still is it equivalent to F or not? We have to check it. Okay. If it is equivalent, then we'll leave it. Okay. So here in this three we have, okay, so three FDs we have. So I have as a B to D is there, D to A is there. Okay. So it means B to A I can achieve by using these two FDs only. So that is B to D is there. Okay, then D to A is there. If I have these two only, okay, so last two, okay, B to D, D to A, it means I can achieve B to A. So no need to keep this one extra here. So whatever first FD is there, this is no need to keep this one. So I can remove this one also. So in the end, what we will get is these two FDs only. That is B to D, D to A. Okay, so now this is my minimal cover. Okay, so whatever given this one is there for this, so this is the minimal cover. So next time just we will go for some algorithms. Stop it here.